Hi. Today the main topic is the B3 part 3. The last video I just talked about what is B3, and I talk about why do we need some kind of B3 and what is the deletion in the B3. I didn't talk about deletion, and I talk about insertion in the B3 and um why database has to store on the disk, and like to get the value from the disk is slow. I talk about those kind of things. So, and I also talk about like the time complexity of the binary tree and the B tree or those kind of thing. I also talk about the limitation of the B tree, which is really kind of bad if there's like range search operation. So we're just gonna like go deep about like the B tree operation, which is the insertion and search and the deletion. But we already talked about search. There's no like more of it, but there's insertion part. So let's begin. Uh, so these are the kind of elements you have to insert. And this is the bit tree. I mean, it looks pretty fine, but the problem is that like it's like here now. When you try to insert, we know that if it's already full, let's say t is the minimum degree is 3, and our the max key is the 2, max key is 3. So the primary key is gonna be 1, right? The primary key index is gonna be 1. So it's pretty fine, but when we're trying to do the insertion part, and like let's say 37, and you now think about, well, when we're trying to insert the 37, since this node is already full, we have to make this 25, which is the primary key, into parent. But those things was really fine because it was kind of easy. But we are definers of the problem that is when we're trying to make 25 into parent, these also the parent keys, the parent node is already full. So let's draw this more. 62 is divided by 25. So 25 goes here. Yes. 25, 54. 25, 54, and 62 here. Yes, that's pretty fine, but we know that this part is already full, and we have to make this the primary key into parent also. So also we have to propagate this split operation also in the parent. So we make 20 as the parent key. So we go here. Now this is how we look. So the before this node is already 4, right? So we just doing the same thing, that we find the primary key index first. If the node, I don't know if you can see or not, so let's put it here. So if node is full, which also means that overflows, make primary key as a parent, which means that just make or sorry, my English is not that good, so or do the split operation, because you have to split, right? So before it was like this, so it was like this, and to draw this kind of B tree into my like TypeScript code or JavaScript code or some kind of random code, this is gonna be like node that has keys which is 4, 20, 25, and 54. And the children is that the key is gonna be node that has key is gonna be 1, node that have key is gonna be 5, node that key is gonna be have 21, node that key is gonna be 32, 27, 62. So this is how you really demonstrate the data structure in the real code. There's no left or right some kind of variable in this B tree. You just have to find using while loop. Let's just try to explain this more. The B tree, the insertion part is kind of easy when you look at it, because just find if it's full, find the primary key and make this as a parent. That's very simple, right? But I think making this kind of logic in using your own program language is really hard. You have to think about recursion thing, and you have to think about like this kind of data structure. So this is how I did. So the train is gonna be some kind of like the parent key, right? So based on this, so this is index 1, right? Based on the 1, you do the split operation, but even on the chart also. So 0, 1, 2, 3, 4, right? So 1, so this one, let's delete this. Let's delete this part. So, and the meaning of split operation is based on this, you have to create the left and right. Since the train is gonna be root, so this one is gonna be left and this one is gonna be right. But also you have to make this left or right on the chart also. But it's kind of really simple. So the index is 0 and 1 and 2, 3. Also based on this, you do the same thing. So this part is gonna be splitted, and this will be the new children of the 4. Let me try to display this kind of more. Yes, you have a node that have keys, which is 4, 20, 25, 54. Since this is already full, you have to make it like this. But this really kind of like the hard thing is that the split operation requires the making a new node. Since this is already one node, it's pretty fine. But if you're trying to make it like this, like the split operation, this is already single node. This one is independent. So you have to make the node, create node operation of it. So this is gonna be, so this data structure, it has to be transformed into like this node that has keys 4. So this is gonna be left, and the 20 is gonna be root. But the right thing is, the data structure is gonna be node had keys, which is 25 and 54. And so the parent is gonna be parent here. So node that had keys gonna be 20 here. So the children part is gonna be this part. Node that has 4, node have is 25 or 54. Like this. So this recursion, you have to create some kind, you have to make a function or the class that creates like create node code to make it like this, and also you have to track all of it. You have to also do the split operation even the children. So because even the left has to have children, right? So based on this one is gonna be children of the left, and this one is the children of the right. So I think this is really kind of hard to implement in your own programming language using of the B-tree. And also the lot of college, they don't really emphasize of like implementing the B-tree of using the programming language. Even there's some kind of implementation of the like using programming language, but it's really old and it's not really readable. So my really generally the recommendation is make some kind of B-tree, some kind of data structure or some kind of indexing algorithm in your programming language. This is gonna be really hard, but I will guarantee that this will make you even thinking that the data structure is not just theory. You can implement it, all of it, and also the comparison of what they told is kind of really like it's not really reality of like software engineering. So that this one, so that was kind of like deep dive of the insertion of the B-tree. But now the next part is that the B-tree, the deletion part. Let's just clean more 20, like 4 and 1 here. So the deletion in the B-tree is more harder than the insertion. The reason why it is more harder than insertion is because you have to think about because the B-tree, the goal is that make the tree as stable, like like the balance. It has to be really balanced. So the purpose of the B-tree is like this. But the deletion, when you try to delete like 62, it's not balanced. So the B-tree has to be like rebalanced based on this. So let's try to begin with the basic thing. So let's delete the key but in the leaf. So this is the leaf, right? So leaf means that there's no children. So there's the last of it. So this is leaf. Like if let's say we want to delete the 32. Our target key is 32. Since we already made B-tree using the key is 2, which means that the max keys are gonna be 3 and the minimum keys is gonna be 1 because t minus 1 is 1. So when you try to delete 32, it's really easy. Delete 32 first, and let's see if this node is underflows. Underflows means that it breaks the rule of the minimum keys. Underflows, which means that length is smaller than the 1. Since this is already stable, there's nothing to do with it. But let's say we wanna delete the key 37. So that is gonna be really hard. But this is already too hard. Let's be like this. Let's say we wanna delete the 21. If we try to delete 21, it's gonna be unbalanced. But so rather than like using like some kind of a really hard, difficult algorithm to balance all of it, we just have to borrow from the siblings. So if the node is underflows, borrow from siblings. Since the sibling is 32, so we can just borrow 32 from here. But the thing you have to care for is we don't really copy the 32 from here. We make a 32 to go to the parent and make 25 go to the bottom. So which means that the 25 is gonna be go here and 32 is gonna be go here. And also the reason why you don't really switch out the 32 in this part because we already had 25 here. If you put 32 on the left of the 25, that breaks the rule of the bit tree. The left part should be smaller. So 25 go to left and 37 go here. That's pretty fine, that's kind of easy. But what if your node is underflow and borrow from the siblings, but what if your siblings also cause underflows? Which also means that our target key is now 37. And what if you're borrowing 37, but when you're trying to delete 37, you have to borrow from the siblings, right? 25 or 62. Even though you borrow from the 25 here, it's already unbalanced. So you have to think about this into another way. So if the siblings are also caused on the flows, you cannot do the some kind of like making balance tree in the leaf part. What you have to do is, if the siblings also cause underflows, borrow from the parent. Since your parent, so 37 is what's here, right? There's 37. Let's like 37 here. Borrow from the parent. Since the parent is the 32, you borrow like this. Delete 32 and merge 25 with the 37. And now our target key is 37. We just delete this. So now we have already balanced the B3 data structure. But this is really kind of like good way. But what if your was it 25? Oh yeah, there was. Wait, was it? Yeah, there was 32, right? So this is what this was 37. But what if what you borrow from the parents also cause underflows? Your parents seems like root or some kind of parent from you from this root of these of the node, but this node is kind of child of this parent. So which also means that you have to carefully look at this if it's caused underflows. The thing we can able to borrow from the parent is because even though we borrow from we get the 32 here, it's already making this 54 the balance. It's not less than 1, right? But what if next our the value have to delete is the 5. Since if you're trying to borrow like delete 5, you cannot really borrow from the siblings, right? So all you have to do is, because the reason why is you cannot borrow from the sibling because it's really independent here. So you get 4 here, and now you delete 5. Since this is already unbalanced because you already deleted 4, you have to do the same stuff that you have to borrow from the 20 because it is already on the flows. Since you get to borrow from the 20, you have to merge it with the 54. So now it's already balanced tree. It's really kind of hard because you have to try off the like if it's like full, if it's created underflows, borrow from the parent. If the parents also cause underflows, it's already borrow from the parents. So those kind of thing is making the B-tree data structure is really hard. But I think the deletion part is kind of really hardest thing in the B-tree. So I think this is it. Have a nice day. See you next time. Bye bye.